All right, so lesson 4 is going to continue our study of limits. And what we've done in the past or in previous lessons is we have found limits numerically by using tables and graphically by using a graph. And so many limits can actually be found with algebraic techniques or tools. And so some of those tools that we're going to be working with is direct substitution, which we've looked at a little bit before, the factor cancellation technique, the conjugate rationalization method, an algebraic manipulation. We're going to be looking at some special trig limits, and then eventually in a future unit, we're going to be working with L'Hopital's rule. And this is another technique for finding limits, but there's some things that we have to kind of get into in another unit before we can bring in L'Hopital's rule. So I want us to talk for just a minute about this substitution theorem. Okay, and I'm going to scoot this up. And the substitution theorem is simply if f is a polynomial function or a rational function. Now remember, a polynomial function is simply a function like this quadratic that we have here. The graph of a polynomial function is continuous over the entire domain of negative infinity to positive infinity. And a rational function is going to be a function like this that perhaps maybe has a hole in the graph or a vertical asymptote. But if you definitely if you have a polynomial function or a rational function, then the limit of the function as x approaches c, some x value, as x gets closer and closer to a value of x, if that limit equals f of c, the same thing you get when you evaluate the function at c, provided that if f is a rational function, the value of the denominator does not equal 0. Okay, so here's what that says. If you have a polynomial function or a rational function and you substitute whatever c is into the function, then the limit of that function will be this f of c, the y value of that point, except if that value makes the denominator equal 0. Okay, and the reason why we have to talk about it this way is that, remember, if you have a rational function, that involves division, and so you know you can't divide by 0. Okay, so here's what we're going to do before we start into this example. When you are evaluating a limit algebraically, whenever you have an example like one of these 6, always try direct substitution first. It is very possible that you can substitute your value of x and get your limit. If that does not result in an actual value, but ends up being like 0 over 0 or infinity over infinity, then we're going to need to, what I say, DMW, which means do more work. That's when we're going to utilize maybe one or more, probably just one of the suggestions that we have here. And that's what we're going to look at with these examples. So let's just go ahead and get into the examples. So I've already done the first one. And the first thing I wanted us to do with this, though, is this. First, recognize that this equation is a quadratic. And we know that the quadratic opens up because the leading coefficient is positive. So we know it's going to open up, and that's basically about all I know, just by looking at the function itself. And what I want to know is I want to know the limit of this function. In other words, what is the y value of this function as x approaches 2? In other words, what y value does this function get very, very close to as x gets very, very close to 2? Now remember, a limit, you have to consider both sides. of that x value. So if this point right here on the graph is has an x value of 2, then we want to find the y value as x approaches 2 from both sides. And so that's what we're looking for, that y value that would be that the function is getting close to as x gets closer to 2. And so directly substituting, I would place 2 in for x and square it, minus 5 times 2 plus 4. And as we work through the number crunching, we'll end up with -2. So what the y value, or the limit of this function as x approaches 2, is -2. And graphically, I got lucky on how I drew my graph. That is the y value that this function is getting very close to as x gets very close to 2. Okay? Okay, so now let's take a look at a rational function. So I want us to find the limit of this function as x approaches 2. So right now I know that the function is a rational function because it's written in the form of a fraction. The other thing I know about the graph of this function is that at x equals -1, the function is undefined. And based on our review of rational functions, we know that there will either be a hole in the graph at -1 or there will be a vertical asymptote. And I could do some more work on this if I need to, but we're going to just substitute first. We need to substitute first to see if we get an actual value. So when I substitute, excuse me, when I substitute the x value of 2, I get 2 cubed plus 1, and I will divide that by 2 plus 1. All right, 2 cubed is 8, 8 plus 1 is 9, 2 plus 1 is 3, excuse me, and that reduces to 3. So, as x approaches 2, the y value of this is 3. So, this is the limit. Notice that when I substituted 2, I got an actual value. And so, if I were to, just to put this in perspective, let me see if I can pull up the graph of this so that we can see this. Let me clear out y equals. In my numerator, I will open my numerator and type in x raised to the 3rd. I will get out of the power. I will add 1. I will close the parentheses. I will divide. And I will open parentheses and then x plus 1. And then I don't know what I graphed last, so I will do a zoom 6. Okay. Okay, so now we have what looks to be a parabola. And just to put this in perspective, remember how we said there would be either a hole or a vertical asymptote at x equals -1? Well, it definitely, here's x equals -1. Doesn't look like there is a vertical asymptote, so it must be a hole, but you might not see the hole. So if I press trace and type in -1, look what happens. So at x equals -1, and I push enter, look at what we get for y. The y value is nothing. So that means that there is a hole in the graph at x equals -1. Okay, so that's just a little review of rational functions. And what I'm really interested in, though, is what y value is this function getting very close to as x gets very close to 2? So I'm in trace, and I will just use my right arrow key my x's are getting bigger, and they're getting closer, okay, getting closer to 1, getting closer to, now look at your y values. The y values are now 1.7. My x is 1.6, my y is 2.1, 1.8, 2.4, 1.9, 2.9. So even here, as x is very close to 2, my y value is very close to 3. And if I'm in trace, if I type in 3 for x and enter, I have x equals 3, y equals 7. So if I use my back arrow key, my x's now are decreasing, and they are getting, well, I just passed it, getting closer and closer to 2. Notice that I've got 2.12, and my y value is 3.37. When I use my back arrow key, it actually gets on the other side of 2. So graphically, you can see where the y values are approaching 3 as x approaches 2. And I could go in and look at the table as well to verify. But the nice thing is that algebraically, we could find that limit as well. Okay? All right, so now let's move on. The limit of the natural log of x over or divided by 3x as x approaches e. Now remember, e is an irrational number, and e is approximately 2.71828, so on, just as a reminder. So I just want to go ahead and substitute e and see what happens. So the natural log of e over 3 times e, well, let's talk about evaluating the natural log of e. The natural log of e has a value of 1. The natural log of e is 1 because, remember, the base of a natural log is understood to be e, and when you see this expression, you're asking yourself, the base e raised to what power equals e? And so this is the power that we're looking for. So I have 1 divided by 3 over e. Now remember, e is not a variable, e is a number. So 1 over 3e is your answer. If you take 3 and multiply it by e, the 2.7, you get whatever that is. So this is a perfectly acceptable answer for C. So the y value of this function, whatever it looks like, is approaching 1 over 3e as x approaches e. Okay? And so all of these so far, we have been able to directly substitute. Let's go ahead and look at this one. Now, this is a cube root function. Hopefully, we kind of remember what a cube root function looks like. And it's not necessarily necessary. We didn't know what this looked like. But this particular function will have a horizontal shift of 4 to the left. So it will look something like this. Not that it matters that we just definitely know what it looks like, but I always like to think about what they look like. But directly substituting, if I directly substitute 4, I'm going to scoot that out of the way. If I substitute 4 for x, then the cube root of 4 plus 4 is the cube root of 8, which is 2. And so there's the y value that this function is getting very close to as x gets very close to 4 is equal to 2. Okay? All right, now let's go back and revisit a trig function, sine of 2 theta. If I directly substitute, then I'm getting, I would have sine of 2 times pi over 6, which is sine of, pi over 3. And now we have to think about what is the sine of pi over 3. Well, remember pi over 3. Pi over 3 would be this angle because, yeah, that's pi over 3. The ordered pair is 1/2 square root of 3 over 2. And so sine of pi over 3 is equal to the square root of 3 over 2. And so there's your limit. And then F, example F, we have an log log. So we have log base 3 of x plus 4. Now let's see what happens when we directly substitute 5. So then I end up with log base 5. No, it's not. Sorry. I'm going to erase. Log base 3 of 5 plus 4. And this is going to be log base 3 of 9. And just like this exponential, take your base of 3. You're asking yourself 3 to what power is equal to 9? And so log base 3 of 9 is equal to 2. And so there's our 6 examples of using direct substitution that yields an exact value, a specific value. So now let's talk about some of these different techniques. So I'm going to go to my next page, page 2. And here's what I want us to think about. Let me bring this down. Okay, so this factor cancellation technique works with rational functions, okay? So if you need to make a note of that, this is useful when you have a rational function and you end up with your limit being 0 over 0 or infinity over infinity. When C makes the denominator of a rational function 0, okay, factor the numerator and denominator to determine if a factor or factors will cancel. If a factor does cancel, then cancel it and substitute directly. All right, so that's what we're going to be looking at. But I want to put something in perspective. I want us to consider this function, x squared plus x minus 6 over x squared minus 6x plus 8. And this is the graph that belongs to this function. Notice that this particular function has a vertical asymptote at 4, and it has a hole at x equals 2. So at x equals 2 and x equals 4. Now let's talk about this graphically for a minute. At x equals 2, if I want to know the y value as x approaches 2, you have to look at it from the left and the right. Does that have a y value that it approaches? And the answer is yes. As you look at this graph coming in from the left, x is getting closer to 2 from the left. It is getting closer to a y value from the it is getting closer to a y value. As you look at this graph coming in from the right, your x's coming in from the right, the x's get closer to 2 from the right, and the graph does approach a y value. So this particular function does have a limit as x approaches 2. And so the question is, what is that value? It almost looks like the value where that hole is -3. But we'll find that out in just a minute. But what if I were to ask you, what is the limit as x approaches 4? So now let's talk about what's going on at 4. Oops, okay. So here we have this vertical asymptote at x equals 4. What is and by the way, I forgot to tell you and remind you that these little branches here do have arrows, even though the calculator did not put them on there. What is the y value of this function as x approaches 4 from the left? Well, notice that from the left, and then we jump over the hole, and then we continue. Your y values are approaching negative infinity. Okay, what about the limit as x approaches 4 from the right? Well, as you come in from the right, x's are getting closer and closer to 4, and your y values are growing in the positive infinity, so the limit would be positive infinity. Now, do these two limits, are they the same? Is the left-hand limit and the right-hand limit, are they the same? And the answer is no. So for the limit, as x approaches 4, the limit does not exist. Because, again, your limit has to approach the same y value from both directions. But how do you notice that or know that from the equation algebraically? Okay, so if I substitute 2 into the numerator and the denominator, let's see what happens. So 2 squared plus 2 minus 6, that's 4 plus 2 minus 6, that equals 0. And then 2 squared minus 6 times 2 plus 8, that's 4 minus 12 plus 8, that's also 0. Notice that we end up with 0 over 0. So what that tells us is that we need to do more DMW, do more work. So what does that mean? Okay, well, this is a rational function, and because it's a rational function, I'm going to try to factor this rational function and see if anything will cancel. So I'm going to rewrite this. The limit as x approaches 2, the numerator will factor into x plus 3 times x minus 2, and the denominator will factor into x minus 4 times x minus 2. Okay, if you notice, do any of the factors cancel? And the answer is yes. So the x minus 2's will cancel. Now that they've canceled, directly substitute or use direct substitution to substitute 2, and let's see what that ends up being. This ends up being 2 plus 3, and in the denominator we have 2 minus 4, and so that's going to be 5 over negative 2. So if we think about that y value right there, the y value is negative, which 5 over negative 2 should be, and that open circle is between 2 and 3, so it makes sense that the limit of this function, the y value of this function, is the y value that is being approached is a negative 5/2 when x is getting closer and closer to 2. So that's the value of the y value where that hole is if that hole wasn't there. Okay? So, that was anytime you have a rational function and you substitute that finite value of 2, if you get 0 over 0 or the infinity over infinity, then you want to do more work. And the idea is if this is a polynomial and this is a polynomial, you will factor and see if anything will cancel. All right, so let's look at a couple of examples using this technique. Okay, so the first thing you want to do is always make sure that you substitute and to see what you get, because if you get an answer, you're done. So substituting 3, we get 3 squared minus 3 minus 6 over 3 squared minus 9. That denominator already tells me I've got a 0 there. 3 squared is 9, 9 minus 3 is 6, so I do have 0 over 0. And so with FRQs, or free response questions, oftentimes you're going to have to show that the direct substitution gives you this 0 over 0, and now you need to show your work that you have to do. So the limit, as x approaches 3, the numerator will factor to x minus 3 times x plus 2. The denominator will factor into x minus 3 times x plus 3. And sure enough, I have this factor of x minus 3 that cancels. And when I substitute, I have 3 plus 2 over 3 plus 3. And that gives me 5 over 6. And that is a finite answer. So there you have it, your limit. Now, whatever this graph looks like, well, I kind of have an idea of what this looks like. Because I have a factor that cancels, the graph at 3 will have a hole in the graph, and at -3, there will be a vertical asymptote. And so the 3 and -3 is the only two x values where you got some issues within the graph. Okay? All right, now let's look at the next. If I substitute 3, I get 3 cubed minus 27. Well, that right there is already 0. And then I have 3 squared plus 3 minus 12. The numerator is 0. I have 3 squared, which is 9, plus 3 is 12. 12 minus 12 is 0. So you're showing here that when you directly substitute, you get 0 over 0. Now let's go about factoring. And again, I know to factor or try to factor because this x cubed minus 27 and x squared plus x minus 12 is a polynomial function. So the limit as x approaches 3. Now this is a difference of cubes. So to factor that difference of cubes, you have a binomial factor of x minus 3, and you have a trinomial factor that will be your x squared. Then your middle term would be x times -3 is -3x, change the sign, plus 3x, and then a -3 squared is plus 9. And then we'll divide that by, now I'm hoping to have a factor of x minus 3 that will cancel. So I have x minus 3 times x plus 4 for the denominator. So now I notice that my x minus 3's will cancel. Now let's see if I can substitute. So if I substitute, I get 3 squared plus 3 times 3 plus 9 over 3 plus 4. And this, I believe, gives us 27 over 7. That's 9. That's not correct. That's not right at all. Or is it? I have 9 plus 9 plus 9. Yeah, that's 27 divided by 7, and that will not reduce. So if I can make my little hiccup go away here. There we go. So I have 27 over 7, and that is your limit. Okay? So one technique is, or one algebraic technique is to substitute, and if you get an answer, you're good. If you end up having a rational function and you end up with like 0 over 0 or like an infinity over infinity, which we haven't had show up yet, that tells you to do more work. So try to factor and cancel and see if that happens, then you go ahead and substitute. So we'll stop this portion of the lesson here, and we will have the next video that will focus on the remainder of the examples and techniques.